Hello, everyone. We are very excited to see you, and we're excited to have Simon today. Before Jovo introduces Simon, a few things. If it's your first time at the Learning Salon, this is an interdisciplinary forum for discussing the contentions and bridges between artificial and biological learning. The audience is very interdisciplinary, and the speakers, we have people from philosophy, from neuroscience, computational disciplines, ML, AI. So if you have a question and something is not clear to you, please feel free to ask a clarification question in the chat. There's an ask a question button below. Please ask your questions there. And after the brief 10 to 20 minute talk, we will discuss, and then we will bring sort of the upvoted questions to the screen to ask your questions. So please ask your questions there and vote on each other's questions. We have a policy of, intellectual disagreement with justification is totally encouraged, but disrespect is not encouraged, although sometimes we joke around, it has to be always free of disrespect. And I have an exciting announcement for next week. So we had a couple of rounds of change of plans, and next week we have a surprising double speaker session where a twin, which is a very well-known Daniel Bassett of neuroscience, and her twin, Perry Zern, are going to give a joint salon. And the salon is going, so Perry Zern is a professor in political philosophy, and Daniel Bassett, as we all know, is in engineering and neuroscience. So they just wrote a book together called Curious Minds. So Perry Zern works on politics and the power of curiosity. And of course, Danny Bassett, we all know her neuroscientific work. So it's going to be very exciting. We're very excited to announce that although you might have seen the older schedule, the schedule has changed. And next week, we're going to have them. So please join us next week for that. With that, I'm passing this on to Jovo, and I request that John also mutes himself so that we can.
I want to hear.
Are you telling me you can hear me on my phone?
I mean, we did hear you, clicking and moving objects around. As always, it's endearing. We love it.
So thank you, Ida. We're so grateful to have Simon here. I've been a big fan of Simon's work for years now. I think one of my favorite parts about his papers is, at least my reading of them, is often like, hey everyone, if you just do this simple thing, it works better than all your complicated stuff, which just makes me happy, because I think a lot of science is kind of secretly art, and we really want to look for the simple solutions that work. And it's easier sometimes to find really complicated engineering systems that work. And Simon seems to have this really artful way of just finding elegant, simple solutions that are clear and easy and understandable, and also better than what everybody else has done. So it makes me happy to read his papers, and I'm super happy to have him here, excited. It's actually the first time I've met him, so I'm excited to meet him, and excited that we all get to talk about whatever he has to say.
All right. So thanks for the introduction, Jovo. And let's see, I assume you can see everything. So today I'm going to talk about a question that I've had for a while. So actually, now I do deep learning research at Google, but before I did deep learning research at Google, I was a neuroscientist, and I studied neural representations in monkeys. And so since moving from neuroscience to deep learning, I've had this question of whether we should be training our computer vision models in ways that are more like the ways that humans and monkeys learn, instead of the seemingly artificial ways that everyone in this field seems to do things. And when I first started at Google, I thought the answer was almost certainly yes. We need to kind of teach our machine learning models in human-like ways. But now I'm pretty sure the answer is no. And I'm going to show you some research that I've done and that others have done, which changed my mind. So the goal of practical computer vision is, broadly speaking, to learn to accurately label images or their constituents using whatever data we can feasibly collect. And so what this means in practice is it's fine if we have to collect a lot of data once. But we don't want to have to collect a lot of data for every single task. And so there's some parallel to human vision here, in that human early visual development takes a really long time. And we have to see a lot of images to actually learn how to interact with the world and perceive the world. But at the same time, like once that's over, we're able to just take a brief glimpse at something, and then we can recognize it forever for the rest of our lives. And so we kind of want to build machine vision systems that are just, they're human in that same way. They're able to accurately identify things based on very few examples. And so the way that we do this in practice in deep learning is through a transfer learning via representation learning. So the basic idea of transfer learning is that we want to use a large data set to improve the performance that we'll get when we're trying to classify or do some other task with some smaller data set. And we do this transfer learning via representation learning. So in representation learning, we train a machine learning model on our large data set so that it gives us some set of features that make it easy to decode useful information. And the amazing thing is that these features make it easy to decode useful information, not just on that large data set, but also on smaller data sets that maybe are a little bit different from that large data set. So just to go into a little more detail about how this works. So generally, in computer vision, when people are learning a representation, there are many ways of doing this, but the most common way is to train machine learning models on the ImageNet 2012 competition data set. So this is a data set of 1.3 million images that belong to 1,000 different classes. And these classes were kind of selected by people to kind of have enough diversity to be representative of the difficulties of real-world vision. And between 2011 and today, accuracy on this data set has skyrocketed. So basically in 2011, the best models we could train did a little bit over 50%. And now we can identify images with over 90% accuracy on this data set. So that's pretty impressive. But then given these models that work extremely well on ImageNet, we have this question of how do we take that representation that we've learned and use it for some other task? And there are two sorts of ways that people typically do this in deep learning. So one way is to take the neural network that we've trained on ImageNet. We freeze the weights of all of the convolutional layers, and then we just retrain the last layer of the network on the representations of the images that are in our smaller data set. And because this last layer of the network is just a linear classifier layer, this is known as linear transfer, or linear evaluation, or linear probe. And this works pretty well, but what works even better is to unfreeze all of those weights in the rest of the network. So basically, we will reinitialize the final layer of the network, and then we'll continue training where we left off on ImageNet, but now we're training on this new smaller data set, which maybe we care more about. So the question that we wanted to answer was, does learning a better supervised model on ImageNet, is that enough to give us a better general representation of images? And so what we did was we took 16 different models trained on ImageNet. So each point here is a different model. And we transferred them to 12 different data sets. So each panel here is a different data set. So the x-axis is the ImageNet accuracy of these 16 models, and the y-axis is how well they do when transferred to these other data sets. And you can see that in every case, there's a pretty strong linear correlation between how well the model did on ImageNet and how well it did on these other data sets. And we tried to pick a representative set of data sets. So we have a data set of food, a data set of birds, data set of scenes, cars, textures. But it doesn't really matter. It seems like no matter what kind of things are in this data set, we always do better with models that perform better on ImageNet. If we average the accuracy across those 12 data sets, we can again make plots that look at compare the correlation between ImageNet accuracy and accuracy transferred to these other data sets, both for the linear transfer setting that I described previously and for the fine-tuning setting. And in both cases, we see that there's a strong correlation. So it seems like we can get more transferable visual representations just by sort of maximizing accuracy on ImageNet. So other researchers have come up with other ways of evaluating the quality.
Simon, I'm sorry to interrupt you a minute, but just because I know it's going to be very important for the rest of your talk, but could you just explain to people just a little bit more exactly what the difference is between the images that you do the second training on versus what's in ImageNet? In other words, are they a subset of the 1,000 types in the next one? It's just, I just think people aren't going to know whether you're trying to make a sort of out of sample claim or whether you're just retraining. Can you just say something exactly what the question is here when you go from ImageNet to this other one? I mean, are there not flowers in ImageNet or cars? So I just think it's important for you to just make people understand exactly what the question is here that's being asked for the transfer.
Yeah, so actually I think like this is really important, and like one of the problems is like if you've already got a data set that's got an enormous number of classes, it's hard to find data sets that don't have any subject level overlap with that data set. But in this case, like ImageNet has flowers in it, but it doesn't have 102 classes of flowers. And ImageNet has cars in it, but this Stanford cars data set has 200 different types of cars that you have to classify according to their make, model, and year. So it still is like a substantially different task from the tasks that we've trained on inside ImageNet. But yeah, I think it's like a valid question, like how different really is one task from another? And I don't think we actually have an objective way of measuring that. I think we can only answer it by kind of appealing to our human notion of similarity between different problems.
So just so I understand, I love being the stand-in for these fictitious people who don't understand in the chat, but it's really just me. But that's fine. So just so I understand, if in ImageNet you only had roses and daisies, right?
Yeah.
And then you have a set of flowers which have 101 other flower types. But in the limit, am I allowed to say that if ImageNet had no flowers in it, that you'd still see this transfer effect in the second smaller data set, even if there wasn't a single flower in ImageNet? Is that right?
Yeah, so I think you would still see the transfer for flowers, but obviously it's like possible to come up with vision tasks where you're not going to get transfer. So I think like if you try to transfer from ImageNet to medical imaging, it seems like it's much harder to get any kind of benefit from pre-training on ImageNet. So it's kind of like this difficult question of how similar is one thing to another. I mean, I think like natural images are similar to other natural images, but there are definitely like things that can come in the form of pixels that are not similar to natural images, if that makes sense.
Yeah, so I'm just trying to understand what's at stake here. Is it really that but in the end, it's some intermediate between similarity and non-similarity that seems to hit the sweet spot? Is that?
Yeah, I think so. I mean, I think like really part of it is like, as machine learning researchers, we don't really care about what data we have or how close it is to the tasks. We care about whether we can get data that's close to the tasks. And so like it seems like we can get data that's close enough to any of the tasks that we will encounter in the real world. And because we can get that data, we're justified in looking at this transfer to practical data sets that are representative of problems that we might encounter when we try to take our computer vision systems and apply them in the real world.
Thank you.
So yeah, to get back to this plot, so here we're looking at the average accuracy across those 12 data sets. And on the x-axis is the ImageNet accuracy, y-axis is average accuracy on of the transferred models. And again, we see like doing better on ImageNet, you get models that transfer substantially better. So other researchers have tried to look at how good these representations derived from ImageNet are in different ways. And one way to do this is to simply try to collect more images that belong to the same classes that are in ImageNet, but maybe are a little more diverse than the images in ImageNet, which were just collected by people doing searches of Flickr back in the 2000s. And so there's one example of this is this ImageNet dataset, where people have been asked to take pictures of chairs, teapots, t-shirts, and 100-something other different things in their home with different backgrounds. And so we can ask, if we have a model that's trained just on ImageNet, how well will it do under distribution shift? How well will it do on these harder images? And so there are a bunch of different data sets like this. And there's a great paper from NeurIPS last year that looks at the correlation between accuracy on ImageNet and the accuracy when we try to classify these shifted data sets, these data sets which have distribution shift from ImageNet. And so the x-axis here is, again, ImageNet accuracy. And now the y-axis is accuracy on some other set of data, other data set, which has classes that belong to ImageNet, but under different conditions. And you can see that you never do as well as you do on the images in ImageNet. It kind of makes sense. If you've only ever seen images in ImageNet, you'll do better classifying other images in ImageNet than you'll do classifying any of these shifted, these distribution shift benchmark data sets. But at the same time, there's a very strong linear correlation between accuracy on ImageNet and accuracy on these other data sets. So it seems like the lesson here is the only way that we have to build better vision models also ends up giving us better ImageNet accuracy. Or to put this another way, just training a better ImageNet model can give us better visual abilities. In practice, what this really means is just training a bigger ImageNet model can give us better visual abilities, because we know that by increasing the number of parameters in the model, we're able to build machine learning models that perform better on ImageNet. So there's still something sort of unsatisfying about learning visual representations from ImageNet. So I guess, like, as a former neuroscientist, it's kind of unsatisfying that we need 1.3 million image level labels. I mean, humans probably don't get 1.3 million labels for anything in their life. And you might also wonder, like, maybe we're learning funny things because we're using all of these labels. Like, maybe there's something weird that happens when you're trying to classify, you're trying to learn a representation by classifying 1,000 classes. So we wanted to come up with a way to learn a good representation without labels. And we did this with contrastive learning. So the idea behind contrastive learning is that we'll learn to map our inputs to an embedding space so that views of the same thing are close and views of different things are far apart in that space. And we can generate these views simply by cropping and distorting static images. So we don't have to go back to the real world. We can do this with a folder full of images. And in practice, the way this works is demonstrated by the animation on the right. We've got two images that we're passing into the model. We create two views of each image by cropping them differently and then distorting their colors. We pass those images through a neural network. And then we learn representations by trying to repel images or views of different images and attract views of the same image. And it turns out that this can learn very good representations. So we developed an approach called SimClear. And the way these approaches are usually evaluated is by first training a representation without any labels, and then training a linear classifier on top of that representation to classify ImageNet. So this is basically a way to benchmark a self-supervised learning algorithm, again, by using an ImageNet classification number. So the x-axis here is the number of parameters in different self-supervised or unsupervised models trained without any labels. And the y-axis is their accuracy on ImageNet after we've trained linear classifiers on top of their representations. And you can see that our approach, SimClear, outperforms all of the methods represented with blue dots, which are other self-supervised, unsupervised learning methods. And it actually is able to match the performance of a supervised ResNet 50 model, although our model needs to be 16 times larger to do that. And it also requires more than 100 times as much computation to train. But given this really good self-supervised representation.
Sorry, can I? So given that the model is 16 times bigger and takes 100 times more, what
so
is
the
the
advantage is that
of
we
it?
haven't used the labels to learn the representation.
I see.
So given this representation, we can again ask how well does it work on other tasks? And it turns out that it transfers as well as a supervised model. And again, as Ida's pointing out, it does take more computation to train than a good supervised model. But it seems like, if anything, the representation that it learns is slightly better than the representation learned through standard supervised learning on ImageNet. So yeah, I think Ida's question is a good one. What do we gain from this? And you might hope that we gain more than just the ability to learn without labels. You might hope that we actually get a more human-like representation. And this is...
Simon, I'm sorry. I'm just again a clarification. You say it's unsupervised, but I couldn't quite see when you took the dog and the bit of a dog and a chair and a bit of a chair. Who decided that those were both the same and the bit of the chair and the chair were the same? I mean, who decided that they should be paired that way?
Yeah, I mean, so I guess we start out with a folder full of images, and we can construct the bits of the dog from one image. So it is kind of like we have a label which says this image is different from this other image.
So that is supervised.
From some perspective, yeah, maybe it's supervised. But I guess, like, as a human...
It's not, John, it's not. That you get that information in unsupervised.
But I just want to know, I just want to know, can we just go back a slide,
yeah,
just so I understand? And I'm not trying to be contentious here, I'm just trying to understand. But when you showed that a dog hind leg and a dog, and then a chair and a bit of a chair, and then, so who paired those two things up to be the same thing? In other words, how did that happen?
So we have like an algorithm that takes in an image, and then it gives us, it randomly crops out part of the image and then distorts that crop. So because we're passing the same image into that algorithm, that's how we know that those two things should be associated with each other. But that's the only kind of label that we have. We don't have the 1,000 class labels that you'd usually get for an ImageNet image.
Right. So you've basically massively compressed the space because of that previous stage, but there is a little bit of manual bit because that splitting into bits, you don't have a dog suddenly mixed up with a bit of a chair or anything like that, right? They're kept.
Yeah, well, yeah, I mean, so we do have the actual, like, we're able to distinguish one example in the data set from another example in the data set, one image from another. So that's something that we have. And we also have like a bit of a manual component to the entire algorithm, in that we have to design the part that takes in an image and then distorts it in different ways. But we don't have the same kind of supervision that we have when we train models in a supervised fashion on ImageNet.
Right. So it's just a little. It's just a different kind of human intervention that isn't the supervision of the classical kind, right?
Yeah.
But there is a human hand on these data in one form or another, right?
Yeah, but I guess there's always some kind of human hand here, right? Like the machine learning models that we're designing, like ultimately humans have to design them. That's why I have a job. And
Right.
I feel like maybe playing around with the input is not that different from playing around with the middle layers, with the architecture of the model that we're training.
Mm-hmm. Mm-hmm.
But John, to be clear, if there was an image in that data space that happened to be of a dog sitting on a chair, his thing would crop it in such a way, and sometimes it would say this image of a dog is the same as the image of a chair, because it doesn't have any semantic labels
Right.
in the data set.
Right.
Okay, any other concerns about whether it's actually unsupervised?
It is actually it is not actually unsupervised, right? So it's not entirely unsupervised. I understand.
So I guess like maybe it would help to know what people think an unsupervised learning algorithm actually would be.
yeah, I always, this is great. This is what this salon really is all about, right? I always imagined that it would be a little bit more like statistical learning, right? That you discern structure in the world, unlabeled, right? That's, that's how I see it.
That is what he's done. That he has done that.
I mean, I guess, yeah, so
Jovo,
Yeah.
we understand, Jovo, that you are on Simon's side, but I think John is making a reasonable point and deserves a proper response, to be honest.
There's no semantic labels in his database. So unsupervised learning is you get a set of points without any semantic labels identifying those points. And supervised learning is you also get a semantic label associated with each of those points. So this is, by that definition, unambiguously unsupervised. Now, I agree with you that it's different than the normal unsupervised. But because there's no semantic labels associated with each point, it's clearly not.
So I think I think John agrees
So,
that it's not the standard supervised learning, but and you agree that it's not as strong as unsupervised learning. That's what I hear. Is that accurate?
I mean, I think the input still is endpoints without any semantic labels, and that's the input to any unsupervised learning algorithm. He happens to have a more clever way of dealing with it, but I define supervised or unsupervised entirely on the basis of what the algorithm gets as input, whether it gets two things per image, which is an image and a label, or one thing per image, which is just the image. And it's
Wasn't John's
just
concern that the one thing is entered in certain kinds of pre-selected lumps or groups?
I mean,
John, I want to ask.
No,
John.
that is actually kind of, yeah, that was, and again, I'm really just, that was what I was worried about. There just seemed to be some structure in the inputting of the images minus labels. I completely get what Jovo's saying, but it just seemed like there was a little bit of sorting of a particular kind going on. Is that wrong, that there's no sorting?
That's how I understood John's point, that there is some sort of sorting. Yes, it's not labeled the same way that classic supervised learning is, but there is some sort of sorting. So it's not just that the agent goes around in the world and starts to categorize on its own. I think that's what John's point.
Yeah, is sorting the wrong word, Simon? I mean, it just felt like there was a sort step.
Yeah, so I guess like in machine learning, this family of methods is called self-supervised learning, and the idea is kind of like we can create a task out of the image in this case, where we know the labels for that task, and then we're training kind of supervised on the task. But we do this without actually like using any more information than you would use in a standard statistical unsupervised learning technique. I mean, like what we're doing here works a lot better than doing PCA on static images, but ultimately you don't need any more information than you would need to do PCA on static images.
Is the number of classes known to the agent?
No, it doesn't know anything.
Yeah, that's John. Would that be kind of like a little better? Because even the number of classes is not known.
Yeah, no, absolutely. Yeah.
It doesn't know even that there are classes.
Yeah.
So, I mean, I think, John, maybe one thing that you're saying that's potentially very interesting is that Simon designed this data set in such a way that it has classes, because there are, in fact, pictures of dogs and chairs and other stuff. Whereas if an agent was wandering around in the world, you would have a continuous stream of images that wouldn't be structured in that way. And so maybe Simon is kind of helping his algorithm learn structure in the world in ways that an unbiased natural observer wouldn't get. And I think that's a fair and very
yes, it felt like
comment.
There was some help being given. That you know what I mean? It just felt like something that past the labels plus images step is in here. It's how it felt, and I'm just not sure whether that's true or not. Is there something that that helped it along?
So I feel like there's nothing that we really know about the data besides that it's made up of images. But we do know that it's made up of images, and that actually is a lot to know. I mean, I guess it means we use algorithms that are meant for images instead of algorithms that are meant for generic data. I guess like there's this other aspect that maybe you could ask, like, what if we had different types of images going in, where if we take two crops, we're unlikely to get two crops of the same object? Like, what if we pass in really big images, where if we take two random crops, we'll end up with crops of different types of objects? Would this algorithm still work? And
Would it?
I think the answer is probably yes, if you tweak the way that the crops are taken out of it. So you probably need to take crops that are close together in the image, which is not a restriction that we've imposed when training this on images from ImageNet.
So, John, are you clear on the contrastive learning aspect of it?
Yes, I actually found that very, very helpful. Yes.
Cool. I do think that, so there are some people in the chat that are saying that they are in the semi-supervised camp, and some people are very strongly in the supervised camp, and there's discussion going on. So maybe we can move on so that Simon gets to finish, and then we come back. I thank you, John, because this is a fantastic discussion. And I think we can continue this for sure and have some people join the screen later, but maybe Simon can finish for the minute.
Yeah, this is great. So yeah, we made an algorithm that can learn without labels, and the representation is about as good as you can get from supervised learning, but it's a lot more expensive. So we next asked, are there other benefits beyond like just not using any labels of training a model in this way? And so one thing that we looked at is this shape texture conflict data set from Robert Garris and colleagues. So this is a data set of images that are constructed so that they have mismatched shape and texture. For example, the image on the left is an elephant textured cat. And if you show these images to people, 96% of the time they would say that image is a cat and not an elephant. But if you show these images to computer vision models, they seem to latch on very strongly to the texture. So we compared a supervised model to several methods that are trained without any labels, including SimClear. And we measured the shape bias, which is the propensity to classify these images according to their shape rather than texture. And you can see these unsupervised models actually do have a stronger propensity to classify by shape. But on the other hand, we trained a supervised model using the same kinds of distortions that we use in SimClear, the same color distortions and the same blurring. And this supervised model actually has a stronger shape bias than the SimClear model. So it seems like actually the qualities of the representations that we're learning maybe have more to do with sort of mundane things or seemingly mundane things we're doing to the data going in than they do with the actual objective that we're using to train the model. And other groups have also looked at the similarity between the predictions of these models on a variety of data sets and human behavior. And these studies have also found that these models actually, self-supervised models trained without any labels, perform similarly to supervised models in terms of human similarity. And actually, they're a lot more like each other than they are like humans. So it doesn't seem like this is a magic recipe to get human-like vision. Actually, it seems like the representations that we've learned share all of the flaws of standard supervised learning with ImageNet labels. So next, we might still hope that there are other gains to get here because self-supervised learning frees us from having to collect labeled data. And there are actually domains where this is extremely useful. So for medical imaging, it's possible to collect data sets where having doctors label images would be very expensive. But if we can learn without those labels, we can get better performing models at much lower costs. The problem is that for natural images, this isn't true. So if we just go out on the internet, we can get a lot of natural images with noisy labels. And if that's okay with us, we can just train a model on those. And so far, it seems like if the data is unlimited, but the model size is fixed, then supervised learning actually seems to still perform better than self-supervised learning. And so what I'm showing here is from a paper from Facebook from earlier this year. And so what they do is they take 1 billion Instagram images, and then they train either a self-supervised model on those images or a supervised model to predict the Instagram hashtags associated with the images. They then take those models and they transfer them to ImageNet. And so what they found is a self-supervised model does a lot better than training a model on ImageNet from scratch if you've trained on these 1 billion images first. But it's even better to train a supervised model to predict those Instagram hashtags. And the Instagram hashtags are effectively free. They don't cost anything. People have just already labeled all of the data for Facebook. So it seems like maybe for natural vision, there's not a huge reason to use self-supervised learning to try to learn without labels. So I guess we could also think about going in the opposite direction and trying to incorporate even more human supervision into these models. And so people have tried to do this by training models on image text pairs, which again, it's information that's free on the internet. So there's a recent paper from OpenAI where they look at how well models trained on these image text pairs transfer, again, to the same 12 data sets that I showed you earlier. And they find that their models trained on image and text perform substantially better than other models that are trained on massive labeled data sets, which in turn perform better than SimClear. So to conclude the presentation, it seems like simply training bigger models is enough to get representations that transfer better and are more robust. And we don't actually have any tricks beyond simply training bigger models. It seems like that's kind of the only thing that works for building better computer vision models at this point. Self-supervised approaches like SimClear can learn representations without labels that rival supervised learning. But it seems like these models require more computation and don't behave qualitatively differently. For natural vision, it turns out that somewhat surprisingly, labels are cheaper than computation. And so we might as well just use all the labels we can get. And that's just the right way to distill human inductive biases into our machine learning models, is just to train big models with as much supervision as possible, which is very different from the way that humans seem to learn, but so far seems to work a lot better than everything else we've tried. So that's the end of my talk. Thanks for listening. And I'd like to thank all of my amazing collaborators without which this wouldn't have been possible.
So thank you so much for that. To your last point, so I don't agree with the way that the last point was framed. Okay, are you hiding? Like
I'm sitting down.
Maybe you want to like pull the camera a little, because like, awesome, now it works. Your last point said the right way to distill human inductive biases into ML would be to train big models with as much supervision as possible. I would say I disagree with this, that this is the right way. Clearly the right way, to me, it's obvious that we need other kinds of architecture, other kinds of models, as opposed to like making the same ones just bigger. One more thing that I wanted to ask is in terms of adversarial images, so not just the cats with texture, with elephant texture, but actual adversarial images. For maybe I can share like maybe I can pull something up so that for people who are not familiar with this, we can clarify what I have in mind or what I mean. Do people see the screen too? No. I don't see it myself, so maybe I go with application window and then figure it out. Well, I'm not figuring out for some reason, so let's see if this will work. Okay, so without showing you the figures, so Goodfellow et al., Claire 2015, and then Brown et al. 2018, they showed examples where if you have a simple panda and maybe the CNN is judging it to be a panda with 60% confidence. You add just a little bit of noise, and there is another image of the panda. To us, it doesn't even look different. We wouldn't even be able to notice the differences. And then all of a sudden, with 99% accuracy, it's associated with, it's classified as a gibbon. And that was Goodfellow et al. Eichler 2015. And then there was another paper by Brown and colleagues in 2018 on adversarial patch. So you have a banana on the screen, and it's classified 99% as a banana. And you just add the sticker patch right next to the banana, not even on top of it. And then all of a sudden, it's classified 99% as a toaster. And so this was these are challenges that CNNs have, convolutional neural networks of vision have. Does your model do better on these two kinds of examples?
So we haven't tested that, but our guess is no, none of these models are adversarially robust, because it seems like the only machine learning models that are ever adversarially robust are those that are specifically trained to be adversarially robust, basically by generating adversarial examples and then encouraging the neural network to give the same output on those examples that it would give on the unperturbed version of those images. And yeah, I think like adversarial examples are an interesting topic. It's not clear to me that the brain doesn't have them. It could just be that we have a very hard time generating them.
So we actually, so not like me, but a number of labs have collected those same data from humans, showing them. And they try to see whether there are situations where humans are making the same kind of adversarial mistakes. And there are situations, there are particular like cat, dog kind, something that is somewhere between cat and dog that people might make a mistake, but it's not the same level like the panda or the adversarial patch kind of examples. And Poggio's lab at MIT did this thing where they had the foveal change, so they didn't allow the CNNs to have the entire image at the same time, but the image had to it had to move in like in a foveal way, the same way that human attention might work, in order to learn the images. And in fact, it improved performance and adversarial robustness. So it was. So I would disagree that same kind of things would go on in the human brain, but.
I mean, so I think it's actually like very complicated to accurately assess how adversarially robust a model is. So if you're thinking of the same Poggio paper that I'm thinking of, yeah, they like basically crop images in different ways, and they show that they can learn a more robust model that way. But it turns out that like most of the defenses against adversarial examples that are not just based on training the model explicitly to be robust to them, but on other kinds of manipulations, most of them can be broken if you instead train the model. Basically, if you design an attack that is specifically tailored to their defense. And so in this case, like if you take an image and you take several crops of the image, if you've designed your adversarial example without taking many crops, then that will actually fix the adversarial example. But if you are instead creating your adversarial example by doing gradient descent, where you're simultaneously taking many crops while you're doing gradient descent, so that each crop actually causes the model to misclassify, then it seems like...
Sorry, just to bring it back to the main point and not get that sort of sideways. The point is that they did experiments with humans and compared humans, not them, like there are a couple of studies, not many, but there are a couple of studies that did compare human behavioral performance and various CNNs. There are some approaches that seem to help a little bit, like the foveal approach of the Poggio lab, but no approach is completely robust. So I'm actually in the camp of, we don't have a good vision model yet. And CNNs are not a good vision model, although they are the best that we have so far. So that's where I was going with this.
I mean, so
however, to answer your question of, we don't have a way to know. Yes, we can have a sets. At least we can compare the human behavior with the same kind of images with a particular network, and we will know whether those particular attacks also hold for humans or not. And from the people who did those experiments, we know that the same kind of attacks are not attacks for human vision in most of the cases. One paper, they reported that if there were some examples that across many different models, these examples were adversarial, then humans were more likely to be also sensitive to them, as opposed to things that were just for one or the other model, to respond to your other point. So there are a lot of things happening in the chat with people talking about visual illusions as adversarial examples for humans. Shahab, that could be the case, but the point here is the comparison. Again, let's go back to the main point. The point is the similarity of the CNN neural network visual performance compared to human vision, so the human likeness. If the only place where there were adversarial challenges for CNNs were indeed the same kind of adversarial situations for humans, like optical illusions, this would have been a good indication. The challenge here is that the adversarial cases for the CNNs are not the same as the ones for humans. So John, you're muted.
Yeah, just to Ida's point, you know, I mean, to say, oh, optical illusions are just the human version of adversarial is to miss, like Ida said, the point entirely, which is, you know, they're very different in kind. And you could argue that optical illusions are due to top-down imposition of priors, which is quite different from the adversarial mistakes that I understand, which are due to the fact that there's something fundamentally dumb about how these systems are doing it from the bottom up. Okay, so in other words, you know, so one is because the level of I mean, somebody asked in the chat, God forbid, once again, what is a representation, right? But representations, I think for everyone would agree that they are some kind of abstraction that allows generalization and flexibility, right? And optical illusions are due to the existence of a quite abstract representation that can make mistakes when it brings itself to bear on a pure stimulus. That is not the same as the representations that you're talking about that are subject to adversarial attack, because they're looking at things from the bottom up, right? They're not imposing an abstraction. Right, so wouldn't you agree that it's just not correct to say, oh, optical illusions are the human versus adversarial, because they come from very different notions of representation, right?
Yeah, I think I agree with that. I don't think that optical illusions are adversarial examples. But I guess maybe I'll.
What are they?
So yeah, what are they? I mean, yeah, I don't think they're necessarily the model being dumb. I mean, I think like the model has basically done its best to learn some function that is able to classify the data. And if you don't have very much data, which I think is like true of the models that we're training, we're not training them on enough data and they're not big enough, then you will learn a whole bunch of features, some of which are actually aligned with the stuff that's in the real world, and others of which are maybe not so aligned with the stuff that actually exists in the real world. And my guess is like humans are not as susceptible, in part because we've just seen more stuff. We know that if you train models on more data, they're kind of naturally more adversarially robust. So maybe like it's just a problem of you need a lot of data to learn robust visual discrimination methods, and we don't have that much data going into our machine learning models.
Yeah, so just, you know, I was one of the advocates of optical illusions are adversarial examples for humans. And so just to support my argument, which, you know, is probably wrong like everything, adversarial examples to me means you are trained on some distribution of data. Then you have either some out of distribution example or an out of distribution another training sample. And so insofar as it doesn't look like the distribution of data you have, it's adversarial. And so optical illusions are clearly that often, right? Sometimes you show a way of looking at things that you don't naturally see. And so in that sense, they are.
So I think it doesn't matter whether we can categorize them as optical illusions or not. That doesn't matter. The argument still holds that CNNs do not show the same kind of things as optical illusions, and they are sensitive. They're sensitivity and failure in the presence of adversarial patches and adversarial examples is not human-like. That's the main point, right?
100%.
Yeah. So I think it's okay I don't think it's very pertinent to the present discussion whether optical illusions are or are not. But I agree that if the only cases where CNNs made an error were the same cases as humans make error in optical illusions, that would have been a good sign. But that's not the case. Okay, John, do you want to ask your questions?
Yeah, I do actually. So just one other thing, if you put something like, this is Puss in Boots or Catwoman into these things, what happens, right? Do they call Catwoman a cat? What happens? Do they, how well do they do in these sort of situations? I'm just curious. Or
they can't have a berry.
Yeah, well, let's not talk about that dreadful. I'm just wondering what happens.
Yeah, I mean, so if you have images that don't belong to any class that that an ImageNet classifier was trained on, then at least in supervised learning, you have this problem where the model will confidently predict something, and it tends not to be anything meaningful. I mean, so it may be that if you pass in Catwoman, you get cat, but it may also be that if you pass in Catwoman, you get like hairspray or something. There are these cases where you just pass people's faces into ImageNet models, and it gives you like very stereotypical gendered outputs because that's how the data set that it was trained on was constructed. So yeah. On the other hand, like if you use the model's representation from this second to last layer, if you use that as a visual similarity metric, if you say, okay, given this image of Catwoman, find me other images that are close in that space, it will generally find images that look very similar to humans and that have the same kind of stuff in them. So even though like the classification part is kind of bogus, like it still seems like it learns representations that generalize well two different types of images.
And also just, so I'm just trying to square what you've said today with the kind of position taken by Rosa Cow and Dan Yeamans and Jim Tocalo, and you know that in fact the representations are very much like what we see in the macaque. And therefore we're on the right track, at least when it comes to object classification. So what am I missing here in terms of, on the one hand, you're saying that this has nothing to do with the way that humans do it. Is that what you're talking about with respect to transfer in particular? Or are you going, I mean, how do I square these two positions? Because now I know people like Dave Susilo and others have said, well, no, this is more about universality. There's something about the structure of the world rather than about the similarity in the organization of the net versus the nervous system. But what am I missing here in terms of the biological convergence versus divergence that you seem to be implying?
So yeah, I guess I don't really have a strong position on whether these systems actually work like brains or not. And I guess I also don't really care. Like I think like my goal is not to build a system that processes information in the same way that a brain does. My goal is to build a system that behaves in the way that a human expects it to. And those could be different goals, and you might not actually need to build a system that is structured in the same way as a brain. And it might even be like trying to build a system that's structured in the same way as a brain. It might cost more in terms of computation, and it might actually be a bad idea if your goal is to replicate human behavior.
Yeah, I guess that wasn't really what I was trying to say. I was just trying to say that on the one hand, we are told, and it's true, that you can predict the tuning properties of neurons in particular layers in the macaque from actually taking a look in a deep neural network, okay? And yet that very same deep neural network makes the kind of mistakes that Ida introduced, the adversarial ones. So I'm just asking, I'm having a bit of cognitive dissonance between, on the one hand, converging on similar tuning to the point that, oh my God, we can predict what the macaque will do, but they make these spectacularly different kind of mistakes, the very same network. So how do I square these two claims, biological verisimilitude on the one hand, and spectacularly different types of mistakes on the other? How do I square those two things? I feel like I'm missing something.
Yeah, I mean, I feel like there's something weird going on where if you pass in images that are from the distribution of natural images on which the model is trained, the model behaves kind of like a brain. And then if you pass in images that are not from that distribution, it's easy to find stuff where the model doesn't behave like a brain. And I don't really have a good answer to why that is.
So you agree that there's something slightly dissonant about that?
I mean, yeah, I think there's something sort of weird, but I don't really know how to think about it.
I have an idea how to think about it, if I may, John. I think the biological verisimilitude, as you so eloquently put it, is overstated. Essentially, and, I was tweeting about this earlier today, that if you a priori establish what the metrics were for establishing similarity across representations, and then you found that, in fact, brains and deep nets were similar, whereas brains and something else were not similar according to that metric, that would be interesting. But I think all of these papers suffer from a kind of cherry picking, where you look at the representations, then you choose a similarity metric, and then you say they are similar. And I could choose a different similarity metric, such as the representations of other objects that they've never seen, and they would be quite different.
I don't find that very satisfactory. I mean, I find Rosa and Dan and quite convincing. I find it quite interesting what they've said about there being some sort of convergence in the within distribution set, like Simon just said. What I wonder, though, is could this be that those are representations that we can derive as experimenters, either from the monkey, we go in there and we as experimenters say, look, it's tuned like this, or as computer scientists, we go in and say, oh, look, it looks like this. But what we don't know is how those representations are actually used in situ by the system. Right? So in other words, is it possible that the adversarial errors are, versus us not making them, are differences in the way that those representations that we as experimenters can extract are actually used by the system? Do you see what I'm saying? In other words, maybe the mistakes are telling us about how these things that we see as third persons are actually being used. Because you can't just assume that that representation is being used within the system, right? In some way it must be. But that's the way I try and reconcile it, is we're missing the sort of retrieval use step of the representation, because the definition of representation is that it has to be used as one, right? It has to function as one. But we're not proving that it's functioning as one when we do these extractions. Do you see what I'm saying? We have to prove that they're actually being used.
So I think like people have probably done this, but I don't know of the research if it's been done. You could look at whether if you try to map a neural network onto a monkey brain, whether if you do that for natural images, if you learn the mapping using natural images, whether that mapping will still work for adversarial images. And I'm pretty sure that you'll find that even if you have a mapping that gives you very good correspondence between your neural network and your monkey brain when you pass in natural images, it will not give you very good correspondence if you pass in adversarial images. So I think it's not just about how the representation is used, it's about how the system actually works.
Yeah, that's what I'm sort of really interested in, is when can one actually think that we're getting insight into the nature of the representation that is then computed on and transformed, right? Versus information, right? I mean, I've used this example before. You can actually decode arm movements from your occipital cortex, but no one thinks you use your occipital cortex to drive arm movements, right? So it's just interesting to me, when is it a representation that's informationally interesting, and when is it actually causally used for the behavior? And maybe sometimes that's the basis for the paradoxes, but maybe you're right in the example you gave. That's not the explanation, because you'd see a big mess in there if you gave an adversarial image to the same layers, and they wouldn't respond anymore in a similar way. And then my last question is just, do you think that this general conclusion about image classification, do you think this is going to be true for everything else we use deep neural networks for, that we're going to use them from learning games to driving cars to, do you think that we're going to end up finding that they're just not doing it the way humans do it? Is that just going to be the general finding across the deep neural network application world?
I mean, I think there's no way that they're going to do it the way that humans do it. I mean, I think like inevitably deep neural networks are going to be better at some things than humans and worse at other things than humans, just because of the way that we've structured them. And I guess like it seems like already we can build neural networks that process text and are able to do some things that a human wouldn't be able to do, but also like can't do a lot of the things that a human can do. So I think it's kind of inevitable, like if you build a system that is at all different from the brain, that it's going to have strengths and weaknesses compared to the brain.
So on that note, the title of your talk seems to suggest something in the order of, what was it again? It's human-like. Do we need human-like learning to show human-like behavior or something like that? Now, you neither have shown human-like behavior nor human-like representations. So I want to see, so I think John's question is well taken. He's changing headphones. Let me wait for John. John, do you hear me? Not yet, I guess. John? Not yet. Do you hear me now? Yes.
Getting a hospital call. Say it again. Yeah. Say it again.
No, I was just saying that to your point, Simon's title was whether we need human-like kind of neural processes or mechanisms in order to have human-like behavior. And that's something that I ask in my kind of work. But so what I understand right now is that we neither saw human-like behavior nor human-like computational representation, right? That's, I feel like the one thing that we, I see in many of John's comments is related to this other question, which is, so we didn't see any of that currently.
Yeah, so I think like we shouldn't expect machine learning models today to act like humans. Like that would mean we've solved all of these like artificial general intelligence problems.
I disagree with that too, because there are some that can perform better than others, and there are some domains that you can have some models that perform there. So I wanted to understand what exactly is the not general comments, but the specific. I feel like that you didn't manage it in your results, but that doesn't sort of transcend to everything that exists, right? We don't need AGI in order to have human-like behavior. We can advance human-like behavior in some domains before reaching AGI. So it doesn't need to be the one that both solves a problem, like solves navigation in a human-like way and ties its shoes. No, we're not going to reach that. But something that behaves in a more human-like way, or let's say navigates in a more human-like way, or categorizes in a more human-like way than what we have, as in it's going to be closer to human behavior, that's achievable.
Can I ask a question about that? I'm sorry, Simon, but I find that really interesting. Do you, on that note, and I'm getting to get myself tied up in knots here. If you manage to get a AI system to act more like a human in a particular domain, isn't acting more like a human in a particular domain just another specialized domain, right? Do you see what I'm saying? Isn't it just another version of a game? And you go, in this game, I want you to learn not how to play Go, but I want you to play Go like a human plays Go, which is just another Go. It's just Go H. But it's still narrow, right?
But that's why I'm saying we don't need AGI for that. I'm saying we can have a more human-like Go player without having AGI.
And what do you think that means, Ida? I'm sorry, Simon, I have to ask this because it's so. If you manage to get a narrow AI that is Go H, which is it's Go like a human, do you think that if you interrogate, and Simon, this gets to the question I asked you, do you think that if you interrogated the representations in the deep layers of Go H versus Go AlphaGo, that there would be a biologically more interesting thing to find in the deep neural network that was domain specific but human-like versus non-human-like and domain specific? In other words, that's a deep issue, right? And I think it's what I think Ida's getting at, which is it is biologically more interesting if you make your deep neural net mimic a human and then go looking at its representations. Would you agree with that? Would you agree with that, Simon?
I mean, so I agree. Like, if you're a neuroscientist, then that is more interesting. But I guess, like, if your goal is to build something that mimics human behavior, I don't think you necessarily have to have any internal representations that look anything like those that a human has.
That's fair, but we don't. That's okay. But the point is that John is making a different point. So again, like, to bring it back to the point that John is making, if you want to look at the representations that a model is using, it would be more interesting to look at or a mechanism, whatever is happening in a model. It would be more interesting to look at a model that does act human-like, even before AGI, than one that doesn't. I think that's the point that John is making.
I mean,
yeah.
So like, how do you make a model that acts like a human but worse in terms of vision? Like, how do you come up? Because, like, the problem is,
I don't understand what you're saying.
So our current models are not as good at computer vision as humans are, right? So that's the problem. So if you're not as good as a human, then it seems like it's difficult to ask these questions about human-like vision as opposed to just better vision.
Sorry, I don't know if there is a communication channel issue, but the point was, once you have a model that does act more human-like than what there is, that was the premise of this discussion that we were having. So imagine model A, it's like a model that you already have. It's not as good as humans. Imagine model B, it has human-level behavior. It's a thought experiment, correct? So
Okay.
Now compare these two. Between these two, John was saying it's more interesting to now look at the underlying mechanisms or representations of model B, because at least it acts more like humans. So you don't need to achieve complete human-like performance. Between two models, one of which is more human-like and one of which less, whatever metric that you have, in a way that is unambiguously more human-like, John is saying that other one is more interesting. I
mean, I agree. Like, if you have a better model, a more human-like model, it's more interesting to look at that model for basically anything.
Jova, do you want to ask your questions, or John, are you done? Or
yeah, I just think the last point Simon was making is you could, even though potentially the representations that you interrogate in the model that does approximate human performance could potentially be biologically a great clue. I mean, it's sort of synthetic neuroscience, right? It's the point that Jim DiCarlo has made. It's possible also, I think, Simon, you were saying that you could mimic a human and still be doing it quite differently.
Yeah, I believe that.
Yeah. This is very interesting. It's a lot of stuff that we've been worrying about for a while. Thank you very much, Simon. I'll hand it over to Jovo. He's champing at the bit.
This is such a joy for me, because I really enjoy talking about these things, and I think these are fundamental questions about what we're even trying to do, right? So do we want to build things that look like humans and perform like humans? I happen to not want that. If I wanted something that performed like a human, I can just make another human. That's
Sorry,
I've done
no,
that a few
that's
times, and they were
no, you can't
perfect.
say this thing. Sorry, it's not. This is not about procreating or giving birth to another human. This is about whether we can have AI that achieves more human-like behavior. If that's not your goal, that's okay. But that is a goal that a lot of people have for for various reasons. So no, the only way to achieve that is not to create another human.
But I don't mean to say it's the only way. I just say I know a way. And what I'm more interested in is building AI that can complement human intelligence and
So
solve
that's not the
problems
title, though, right? The
that we
title of
can't
this
solve.
talk, however, was about whether we need human-like mechanisms in order to have human-like behavior. So you're very, of course, welcome to ask questions about something else, but but at some point it would be good to connect it to the title of the talk too.
I'm happy to talk about this. I mean, I think that his talk raises these issues, and so maybe he didn't talk about this particular issue, but I think it's on point for the Salon of what we're trying to do with AI and why we're trying to do it. I think to John's point, I think that one thing that's missing maybe is this idea of the natural statistics of images. So if you take just natural images and do something really kind of archaic, like passing through a Fourier, like just do a Fourier transform on them, you get things that look like Gabor filters. So there's layers in neural networks that are kind of fundamental on the basis of the natural statistics. And so people have thought for a while about whether that's interesting or not, that the first layers kind of look like that. And I think it kind of depends on your perspective. It's a property of sparse coding, basically an efficient representation of natural statistics, that you would get whatever the representation is. And so then you can ask about the deeper layers, and that I think is more interesting. But some layers looking the same across humans and deep learning, well, they also look the same as basically everything else. And so those representations I don't find particularly interesting or insightful. In terms of Simon's talk, no, I don't have any specific questions. I think John asked a lot of questions, and there's a lot of other people that have a lot of questions. I'd rather kind of hear from them. So I cede the floor. Oh, we lost Ida. John's
went to get some water. She went to get some water. So
okay.
yeah, so maybe Simon, that's awesome. Yeah, there's a lot of questions in chat, so we should just shut up and let everybody in, I think. How do you want to do this, Jovo? The top voted question.
Sure.
Oh, it's it's about representations. Oh my God.
I think you're going to be okay. I'll invite Jason.
I invite Jason in to talk to Simon. Yeah. Mm-hmm. He got the 2 top questions, so he definitely needs to come in.
Yeah, I invited Jason.
And maybe Alex?
Sure. And I guess they're logging in now. There we go. Yeah. Jason's logging in. We're waiting for Alex. You didn't really ask your questions yet.
To be honest, I think it's best to just go to the questions of the audience.
Oh, I'm making noises. So I'm going to get told off.
No, it sounds great, John. This is like the interlude.
Do you know? I think I've mentioned this before. In England, in the movies, before the movie started, there was this big thing that would go up, which would say, "Would patrons kindly refrain from making infantile slurping noises during the movie?" And then everyone would do so. Anyway.
Hello, Alex.
Hey. I guess you invited me to ask the question I asked in the list, right?
You can talk about whatever you like.
Oh, well.
Well, sorry. The goal is that you would ask the question you asked that was highly voted. You can call John later and talk to him about whatever.
Yeah, that was a very specific question from the beginning of the talk that didn't come in the discussion afterwards. was about the comparisons between models trained on ImageNet and models trained on other datasets. I was wondering about any potential catastrophic forgetting if you measure that. So the accuracy on ImageNet that you report in the plots is measured. Is the original ImageNet accuracy, or is the accuracy measured after fine-tuning? Yeah, I'm talking about fine-tuning models, not the linear models.
Yeah, so like after fine-tuning models on other data sets, they tend to a lot of the stuff that was important on ImageNet. And I guess like you could think about like jointly training, like continuing to train on ImageNet along with training on the other data set. But that's not something that we've ever tried. My guess is you can probably, if you're willing to keep ImageNet around and keep training on everything, you could probably avoid the catastrophic forgetting. But like a lot of the time, we don't really care about like making a copy of the model so that like when we're fine tuning it on the new data set, we don't have to worry about forgetting all of the knowledge from ImageNet that wasn't relevant to that new data set.
Well, I could. Yeah, I mean that's not scalable, right? I could think of scenarios where it would be important to keep the original performance.
I think
if you're learning, we're learning like different classes, for example, of objects, and we have a very good performance with say 1,000 classes, but there's more. There's like near not infinite, but there's so many different categories that we would be interested in discriminating in the hierarchy. It would be good to keep the models performing well with the original representations.
So I guess like the way that I think of things, like basically if we're able to get 1 billion images, 10 billion images, and pre-train the model on that, then like the tasks that we actually care about, we're inevitably going to have so few images for that it's not worth like trying to continue training on all of the other tasks that we actually care about. We could just pre-train the model on that 10 billion image data set, copy it, fine-tune it on that on our whatever 1,000 image data set. We have another 1,000 image data set. We just copy that 10 billion image pre-trained model again. Like there's no real point in taking the model, which has now seen 10 billion images plus another 1,000 images, and continuing to train it on that new data set.
Yeah, I can see that from an engineering point of view. That could do the work, but to me it's like a sign. If we relate it to neuroscience, it's a sign that something is wrong. In like, if we think of it in how humans perform this task, it's definitely not like that. We are reusing the information we learn from the subsequent tasks. So I agree with you. Like if the sole purpose of it is to keep performing well on a very well-defined scenario, then sure. But it to me it is telling that something in the way the model is learned is, well, at least there's room for improvement, I would say.
I mean, I totally agree with you. I mean, I think like the way we're doing it now, it's not like the way humans learn, and like catastrophic forgetting is like a real difference between machine learning and human learning. But on the other hand, I feel like for practical computer vision, it basically doesn't matter. We can end up with models that still work just fine despite all of these flaws.
Right.
I mean, it's funny, right? Because not only is there this issue about the similarities in the tuning and the contradiction with respect to the adversarial mistakes, but then you have something like at Princeton, Yuri Hassan writing that, in fact, you do sample lots and lots of stuff in your life, and you are just brute force training your deep neural networks, and what looks like extrapolation is really interpolation. And we are learning something fundamental, which is that life is about lots of data, and that is what we're doing, and we're not very good at most animals, actually, and Jova and I have been talking about this, are not that great, actually. Don't just forget about humans for a second, because Yuri in his paper admits that we don't know about system 2. He also says that, but he says, you know, in other animals, they don't generalize that well. They're just very well Tony Zeta, they have their wiring and then they learn like deep neural nets do. And most of their lives, they do little bits of interpolation. So there are people who are arguing the opposite. So is the paradox here, paradox number two, humans versus deep neural nets? Or is it also true of mice versus deep neural nets? In other words, would we disagree with the Yuri Hassan paper that you shouldn't be seeing the parallels to the degree that they wrote about in that paper, that it is that? I mean, and it's, or do you agree that it's just the human difference we're worrying about here? Which one is it?
John, are you talking about rodent vision? Because mice don't have a good
not vision. I wasn't talking about vision. I was just talking about in general, you know, this idea of training with a lot of data, being able to be quite good within sample, and that if the sample's big enough, then you're not going to come across many surprises when you're a little gerbil in the desert, right? Maybe it is what a lot of animals do, right? I mean, so I'm just trying to distinguish between human vision and where we've unequivocally agreed that they're not the same. But what about the argument that a lot of life is just brute force training and interpolation? Are you sympathetic with that?
Sorry, can I interject for a second? Isn't that very general and not so? Generally, we need a lot of examples and training, but we know that at some point, one-shot learning or zero-shot learning happens in humans, and we are not there with sort of with deep learning there. And we don't know, so Simon made a very good point of having 1.2 million labeled samples. I mean, we don't know if really humans get that many samples.
Sure.
Two, right? When they actually start to distinguish or name objects. I don't know, is it one or two? I don't know about development.
Well, I was just saying that I agree. I think we've all agreed that it doesn't really work for humans in the visual case. I'm just trying to generalize the discussion a bit more, which is that there are people like in that paper, right, who have thought that maybe getting away from human system 2 type cognition, that you just do a lot of training and life is interpolation, right? And if you're a gerbil and you're unlucky enough to be dropped in the Arctic, you'll be dead within seconds, right? So I'm just wondering whether there is more of a convergence on biological systems once we get away from comparing the specific case of vision in humans. That's what I was just trying to get at. Simon.
Yeah, I mean, I guess I don't have a super strong opinion on this. I mean, I think like probably like there are going to be some differences between our machine learning models and like any kind of natural organism, because like monkeys are also trained on different kinds of inputs than our machine learning models are. So at least the stuff that we've got right now, there's going to be a difference. But I think like, again, like we can, the way to overcome these differences is like train on more data. I mean, I think like there's all this stuff that we've got built into our biological systems that we've basically, that has been found through evolution and that probably is useful for doing these kinds of tasks. And that means that because our machine learning models they're not born knowing that stuff like we are, or that like monkeys are, like other organisms are. That means that they are going to need more data to actually figure out how to do stuff. But it doesn't mean that it's impossible.
So
Yeah.
John Kuby says something in the chat that I think it relates to some discussions that we've been having with various sort of, there was a recent meta-learning workshop with Peter Dayan, Matt Botvinnik, Tim Behrens was there. He was earlier in this chat too. I don't know if he's still there. Jane Wang had organized it earlier this week. And we discussed a lot about priors being something akin to evolutionary outer loop meta-learning. And John Kuby is just mentioning in the chat that gerbils and other animals likely are born with more priors rather than fewer. And he's saying this in response to the question that John asked, and I agree with him, that it's not just about brute force data in one lifetime. So if we are talking about meta learning happening and endowing some sort of architecture to the agent or to the sort of the animal, that's a different level of data that we're talking about, as opposed to data within one lifetime. So a lot of the biases are not something that you learn necessarily, or something that you just have because of the architecture, and some of them you might acquire over a lifetime. And I think it's important to distinguish between them. I wouldn't discuss Uri Hassan's paper here, but this general argument by people who work in this field, I think is very valid, that there are some things that you learn, but there are some things that your architecture has acquired in that outer loop meta learning throughout evolution. And I think Jane Wang said some stuff about that in her session as well. And I thank John Kubi for mentioning that, because I think that's really related. I just realized when I say +1 John, if there are 3 Johns in the talking, it's not clear who it is.
Usually I know it's not going to be me.
I say +1 too.
I'm joking. I know, of course you do.
And your Arctic Gerbil band.
I know, the Arctic Gerbils, we're great.
Yeah, there you
go. All right.
If I can add something to that, like I think actually the connection that John made between Uri Hassan's paper and the conclusion from Simon's presentation, I think it's quite relevant here, which is about this idea of interpolation. And you mentioned brute force and having more data, more supervision, which I agree. But I think it's also very important to take into account constraints and how the human brain and organisms in general are really constrained. Like the fact that we do a lot of supervision and more data doesn't mean that, and brute force doesn't mean that we learn everything. We are really, really constrained on what is important and what is not, and what has to be learned, and what is not. And that's why we have probably as well optical illusions and so on, because this kind of stuff is not relevant for the task we have to perform. And also adversarial examples, which is a different thing to me as well, but because the models were not trained on that sort of task, they don't have yet these sort of constraints that are relevant for humans, for example.
Yeah. Mm-hmm.
I think John's question also kind of brings up a more general question, which is, what's going on in the sense of one explanation is we're built with better priors, and through evolutionary processes, we just have better priors for the natural world. Another one is somehow we're more effective at leveraging unlabeled data and using self-supervised techniques. Another option is we're better using supervised data, and that's another one. I'm sure there are others, but we use better training examples, or we have a better curriculum. Like we can sort the training data in a way that enables us to learn faster, which is, in human learning, it's clearly a very big deal, is the order in which you learn concepts, which for most of machine learning has kind of been ignored. So there's all these possibilities about why humans are doing better. And I think this talk brings up that it's not at all clear what is the reason. And there's lots of cool stuff to explore there.
Yeah.
Sorry, can you repeat that, Joe? What you said? What is the?
So one option is humans get more unlabeled data than we're giving these machines. One option is we use that unlabeled data more effectively. We have more efficient learning algorithms as a function of the unlabeled sample size. One is we have better priors for the natural world. And so we kind of start out knowing more relevant stuff. And so we don't have as far to go.
I think another thing is that the data that we receive has correlation with one another and in time in ways that data that are just these images that were sent don't have. So if I see a dog right now, it doesn't disappear and a hair shows up. It's mostly like, if it disappears, it's because it went behind something, and if I move, I will find it. Or if it doesn't, even a baby that is born, if a dog goes behind something and doesn't come out or it disappears, they get surprised. So even babies get surprised if something doesn't show sort of some kind of basic physics properties. So I think that I agree that there is something about the algorithms. The algorithms need to be different. So I disagree that we just need bigger algorithms of the same kind with more data. I think we just need different kinds of algorithms. We need to be more creative about it. And if we want to we want to learn some biases. Some of them could be learned in a meta-learning evolutionary kind of way. And some of them can, I also prefer that kind of learning of biases as opposed to the symbolic AI approach, which is just inbuild the biases. I prefer that it's learned to some extent, even if it's learned at the evolutionary level. And the other thing is that the kind of data that we are providing, is it helpful that we're providing data that's not correlated in time with one another or has no relationship with one another, as opposed to data that's in the real world where there is a way that if I move around the chair, there are certain contingencies. So after a while, I can interpolate based on the fact that I know I have 3D imagination of what objects would look like from different sides. I don't need to see the different parts. I can just imagine the different sides of it by seeing some parts. But yeah, so algorithms and biases being acquired, and data that's maybe more correlated as opposed to just more, or more naturalistic as opposed to being. I think. Oh, Simon.
Yeah.
Go ahead.
So do you want me to talk first about the video thing or the meta learning thing?
I mean, whichever you think you can more directly address.
Okay, so for video, I mean, so yeah, it's true that humans see all of this temporally correlated information, and like, I guess the thing is, unless there's information that you can only get from video, it doesn't seem computationally efficient.
Sorry, I didn't mean video. I mean that I'm moving around, right? So it's kind of an interactive thing. So it's not just that it's a video, it's the fact, it's more like a 3D game as opposed to a video, I guess. Because you can move around an object and you can see where the object goes, you can interact, you can test hypothesis by, going behind the wall, coming back and seeing if things change, etc.
Yeah, so I guess what I would say is it only makes sense to use temporally correlated inputs in a machine learning model if you think that you can learn more from temporally correlated inputs than you could from the same number of inputs if they were not correlated. And so like if you think about a billion frames of video versus a billion images with text captions, or like a billion frames of interacting with an environment versus a billion images with text captions, it seems like there's going to be more information in a billion static images with text captions, unless there's something very particular that you can only get through interacting with the environment. And because of that, I think if you're ultimately limited by computation, you're still going to be better off just learning from static data.
I don't understand that reasoning, but I think we can move on to the next thing. And we did try to, Andrew Sachs is here. So why don't we invite Andrew? Andrew has done a lot of work. Mihai says he's still around. So if you can invite Mihai and Andrew, that would be great.
Thank you, Alex.
Thank you, Alex.
Thanks.
Thank you, Alex.
Chaz unfortunately had a baby. I mean, he can show up with a baby, we don't mind, but I think he might be too distracted. We've had people with a baby in arm before.
I think I've had a baby in arm before. I'm those people.
Yeah, you're one of those people.
I don't. If I may multi-scale what you just said, not just temporal local correlations, but just generally just a curriculum of educating, I think is a wide open thing in machine learning right now.
As well as lifelong learning in general.
Yeah.
I think, and you doing some work on that. I think that's very relevant here. Hello, Mihai.
Hello.
Hello there, can you hear me? Cool.
Yeah.
Yeah, thanks. So the title of the talk refers to acting like humans. And I was just wondering if, if you are talking about this in a strict sense, so do you care about acting like humans? About just performing actions well in a general sense, in an AGI sense. So your models be used more for acting like a human as opposed to, say, acting more like a squirrel or more like a dolphin.
So I think like we probably generally care more about just getting accurate information from an image than we do about acting exactly like a human. On the other hand, the way that we evaluate our machine learning models and the way that we train our machine learning models is using labels produced by humans. So ultimately, the evaluation is always like, does our machine learning model give the same output when it receives this image as a human does? So I think it's kind of like difficult to separate this general question of is the model accurate versus is the model like a human, because we don't have an independent way of measuring accuracy, at least on most kinds of computer vision data sets.
Well, I guess my question is more direct towards action in a way. So how could these models best support action that is most like human as opposed to just like generally perform well? Is that the question, or are you just trying to generally perform well? So let's say if we have a bat and we have a data set with just bat-like stuff, then the same models could be used to do like more bat-like things. So the bias here is just that the data is gathered by humans, so presumably we'll obtain more human-like action, right?
Yeah, I mean, I guess like usually we're just training these models without any kind of notion of what kind of action is going to happen later. Like the idea is we're just doing the perception part. We're just going from images to labels. So I guess it's kind of hard then to think about like how visual representation should differ depending on the types of actions that you want to do.
Well, I'm not sure if this might be opening up a big discussion people might not want to get into, but do you think those can really be separated, or is action like, does action have to be really closely tied onto how you might be representing the world you're seeing? Or are they just independent, completely separable?
So maybe they're not completely separable. I guess like if you have a model and the model has a finite size, then the model has to focus more on some things than other things. And so you might think that like depending on the actions, depending on the stuff you want to do with the model, like the model should represent different aspects of the world. But I think like I do believe that it's possible to train a reasonably general representation that can do a lot of stuff.
Yeah, thanks. I think that answers my questions. Thanks very much.
Thank you.
Hello, Andrew Sachs. For some
Hello.
reason, as soon as it was your turn, Jovo just disappeared. His Wi-Fi is going a little funky. Go ahead.
Yeah, so thanks. This is really interesting. I guess I'm wondering, it feels like a lot of the discussion is turning around, you know, there are places where behavior doesn't match human behavior. There are places where these models don't match neural behavior. But like, is there room for incrementalism? Is there room for saying, yes, they don't capture anything, but they're a really interesting piece of the puzzle? And yeah, so I guess that's the broader question I'm curious if you have thoughts on. But the one thing that came up in the chat, just a small thing, is someone was asking about hierarchical learning processes. And you know, that is something deep networks show. You train them on ImageNet, you see this differentiation through hierarchical structure, and that's also true in toy models. And so that's maybe another axis of comparison. You don't just have to compare the end representation of the model, you can also compare their representation over learning. And it seems like these models, they're simple, but they're capturing maybe some features that you see in biological models.
But Andrew, I guess thinking about this, right, again, coming back to these intermediate representations that seem to have some kind of parallel to the ones in mammalian cortex, do you think that there's a difference between a certain inevitability where, you know, the world has a certain statistical structure, you're talking about the sensory modality when things first come in before you get to perception, where there's almost no choice, that the world has to have this kind of structure, and there's a nice homomorphism between deep layered structures and the visual statistics of the world. But when it gets interesting is when you have options, when there's different ways that one could potentially represent a task or a situation, where you're no longer beholden in some way, tethered to the statistics of the world. You've got options. And that's when we begin to see the divergence. Would you agree that that's where we don't really know what to do, is when you have options, right? And you've got people who say under constraints, you have to come up with different representations when you don't have lots of compute and lots of data. And suddenly as a byproduct, you get common sense, right? Versus if you had lots of compute and lots of data, you never have to find that because you can do it the way vision is done. So it seems to me that maybe one of the reasons why we're having these divergences is when there's a kind of homomorphism that's sort of universal, whether you're a computer or a visual cortex. But suddenly when we get into the world of problem solving, there are just lots of options and the divergences cease to be as useful. Do you see what I'm saying? Do you think it's something like that?
Yeah, I mean, well, absolutely. And there's so many like potential, I mean, just as a simple example, like if you're computing the Fourier transform, right, that specifies how inputs relate to outputs and is very simple. And you can do that using the Fourier transform, but you can also do it using the fast Fourier transform. And if you write those down as neural networks, one of those is shallow network, one of those is deep network, but the deep network is super sparse. And so you've done the computation completely differently. The internal representations are totally different, but the overall function is identical, and one is way sparser. So I guess to me, possibly the way out is to say we're going to have to start adding principles. It's not just about the function you're computing. We add new constraints to the model, in this case, maybe something like sparsity. And then maybe you could start getting some additional matches. But the other thing I would say is, like, you know, people can be interested in different things. So you may be willing to say, no, all of those representations that allow you to compute the right input-output function, I'm just going to call those the same. I mean, that's a move you could make, right? And then you'd be operating on a different level of detail that you wouldn't need to necessarily model all details of the representation. And if all you cared about is the input-output function, then maybe that's the way to go.
So I think that that's a very well taken point, but I want to again bring it back to the title of this talk, right? So the idea is whether we need human-like mechanisms in order to have human-like behavior. And so while there are a lot of interesting questions out there, I was hoping to focus on this particular one here, which is something that some of us are sort of, a lot of us are interested in. There are definitely a million other very interesting questions in this domain. And I fully agree that sometimes it's interesting to analyze neural networks just for the sake of the math, to be honest with you. I am on the camp of beauty is enough reasons to do something, and there's beautiful math going on there, and I'm not ashamed of saying this. But then on the other hand, there is the time where it's not the math beauty hat, but it's the I want human-like behavior hat. And this could be for the sake of interest in neuroscience, or this could be because literally we are designing avatars that need to behave like humans in a game. And the user wants this, or the players, the human players want this avatar to play with them in a human-like way, right? So whether it's that reason, or whether it's because we want to understand human-like behavior, whether you want to do both and use one for the other purpose, all of the above are various situations where you actually want to measure human-like performance in more than one very constrained thing. It's at the end of the day, John is correct that it's still going to be not as specialized as AGI, and I'm fine with it, because we didn't say, how do we reach AGI? We were just saying, how do we reach human-like behavior in certain domains that's more than just very, very specific, like a little bit more, like it has a little bit more of a generalization or out of distribution behavior, but it doesn't need to also tie its shoes. Like it's okay if it's just doing navigation in a game, right? Or a visual categorization. So in that sense, I'm very much with you that there could be different goals, but I do still think it's important to also focus sometimes on the goal of human-like behavior and human-like mechanisms. And I agree with you that the approach that might get us there is to add some principles as opposed to just make things bigger or more training. I agree with you. I think I'm on your camp in that sense that maybe, and to be honest, I think some of the discovery with the beautiful math that one does just for the sake of it sometimes comes handy, because you discover some tools and you're like, oh, this is a tool that if I add to this network, it could do this thing. It could become, more hierarchical or more sparse. Does that make sense? The addendum to the comment that you made.
Yeah, can I just make a quick clarification? So the title of the talk is about whether our machines need to learn like humans. So not necessarily whether they have to have architectures like humans, but whether we have to train them in the same way on the same data.
Right.
And so I think actually those are different questions.
Sorry, but the constraint is learn like humans for human-like behavior, right? That was still the concern. So
yes.
The term learn like human, I kind of paraphrased it as have human-like mechanisms, but I can say it, I will correct it to say have human-like learning mechanisms, but maybe you even don't need mechanisms, because I don't know how, the meaning of learning like humans, it could have different meanings. So I will just correct, instead of saying having human-like mechanisms, we'll say having human-like learning. But even then, it translates to some architecture when we are talking about ML and AI. Having a human-like learning, it's one kind of architecture, I guess, or one kind of learning principle, or a series of learning principles. And let's call that set the set of human-like learning principles, right?
I mean, I feel like we can have different architectures that learn the same way, and we can have the same architecture and make it learn in different ways by giving it different data or different objective, right?
Okay, so if you're saying human-like learning, then different objective, I'm not sure about that, but the point is there is a set of principles, architectures, what you want to call it, and this set is the human-like learning. Does that make sense?
So I guess what I'm thinking of is specifically data and objective. Like, do we need our machine learning model to get the same kind of data that humans get and to end up doing something like what humans do in order for it to learn representations, or learn basically not representations, but just how to act like a human?
So you don't even mean human-like learning. You just mean receiving the same data as humans receive? I'm very confused now about everything about this conversation.
So maybe the question is about what it means to learn then? I mean, I feel like...
I think learning doesn't mean data. Learning means, that would be curriculum learning if you provide us. But anyway, this is not the kind of conversation we usually have, but maybe somebody else want to take over. John, you're muted.
Yeah, I was just wondering if Andrew wanted, I feel like he made his one point, but he's in here. Andrew, was there anything else in the discussion that you felt you wanted to comment on while you're here?
No, not really, but thanks for having me. I think I see Simon's point here, Ida. Like,
oh, go ahead.
Just the data, right? Like a human gets a very specific curriculum, starting with like, their sippy cup, like every single view of their sippy cup, right? And then progresses on from there. And I think if I'm following you, Simon, you're saying like, you don't need to do that to get human-like behavior, possibly. You could just give them 60 billion static images of every cup ever made and train it in a very different way, but still wind up with human-like behavior. I don't know, that seems possible, yeah.
Right. So if then I guess I wouldn't call it human-like learning, or maybe it would be curriculum regime or data. I don't know. Like that would be a bit different. If I say human-like learning, I would mean the mechanism by which, or the learning principles by which something learns. The same way that if I say reinforcement learning, I don't mean the data that it receives. I actually mean, for instance, temporal difference learning, model-based learning, success representation learning, I don't know, like contextual bandits. So that's what we mean when, at least when I talk about that. Or when we say machine learning, we don't necessarily mean the kind of data or the curriculum of the data fed, but we mean different learning principles. So, and if we say learning in the brain, we mean plasticity. We could mean like error-based learning. We could mean various kinds of things. Is there somebody else in here that maybe Zena can come to the screen next? Oh, John, you're muted.
Rosa, we can invite Rosa in. We brought her up before. Maybe
Yeah,
she could,
yeah, of
because
course.
Rosa could actually maybe get maybe Rosa could
Yeah, let's
clarify
have Rosa.
the paradox between it being very human-like and yet what Simon's saying it's not.
Well, it's not human-like, right? So currently we don't have a human-like thing yet.
No, but the argument I'm just saying what Rosa and Dan and others have said, which is there is a neural level convergence, and so there's a behavioral divergence, and yet there seems to be neural convergence.
Yes, I agree.
Yeah,
Yes,
and Rosa gave a great talk I heard recently about that.
Rosa, would you join the screen?
She
I
said
think
no.
there's a delay.
There's probably a theory question.
Go on.
Has this already been answered? Do we know, like, does there exist a data set that drives a deep network to any set of weights you want? Because then the answer is almost certainly, well, maybe not. I was thinking if that's true, then like there's some data set that will get you to any end position you want to get to, right? Whatever human-like mechanisms happen to be, you can generate the data set that would get you there, and then train the network on that.
I think there are certain kinds of learning principles that if you don't have them, or if you have very basic learning principles, there's not enough. So what you're saying is, with any simple learning mechanism, is there a data set possible that if we trained that learner with that set of data, it will learn anything?
I mean, sure, but say it's gradient descent. Say you're willing for it to be supervised gradient descent, then then that would say like, well, no, maybe you don't need the exact data that a human got because you could always push the system there using some other
So
data set.
I agree that we don't need the exact data that humans got in order to have human-like behavior. I don't disagree with that. I also don't disagree that we could have human-like behavior without human-like learning mechanisms. What I disagree with is that the way to get, which was the last bullet point that Simon had on his slides, which is that in order to achieve more human-like behavior, what we need is more training and larger models of the same kind we've had. I disagree with that comment. But I fully agree that we could have human-like behavior without human-like mechanisms and human-like behavior without the same kind of data that humans have had in their lifetime. That's a premise of a lot of things that I do. I don't know if many people disagree with that. So I don't think that that's, I feel like that's the assumption all of us have for building any kind of models. But then it seems to me that the details matter here, and also the general, I don't know. There are other things that I would disagree with. Like, I disagree with just having bigger models with just more training. I don't think that's the approach to go.
Yeah, me too. Although I will say I've been very impressed by just how good big models are. I mean, it's pretty remarkable.
Yeah, it's very impressive, but I agree. I fully agree. And also Simon's work is very impressive, but I
guess like my perspective on this is that we know that if we have a bigger model and we train it on more data, that it will learn something. It will learn like a better function, right? Like, assuming data is not limited and the problem is computation, then just making the model bigger will give us a function in the end that is closer to the one that we're trying to approximate.
I think there's a bias variance trade-off issue here, which I'm sure Andrew would like to talk about also. But bigger models eventually, depending if you have enough computation, they'll just overfit entirely. But
we're not in the limited data regime. We have like a virtually unlimited amount of data on the internet, so we're not going to overfit it.
I think if for any fixed finite amount of data, if you have an infinite amount of computation, you run SGD for forever, it will learn the optimal set of weights for that data set, which will in fact overfit it.
So that's true, but we're not like anywhere near that regime. We're in the regime where we don't have enough compute to process all of the data that we could look at even once.
Andrew, what do you think about all this?
I think well, It's slippery because regularization is another way of stopping a model from overfitting. So you could have absolutely here's one. A RBF kernel SVM corresponds to infinite features, right? So that's a way bigger model than any data set you'll ever have because it's infinite, right? And still, it's going to generalize just fine. And the reason why is because you regularized it. So you look for the maximum margin solution. And gradient descent is no different. If you start it with small weights, then when you train the network, they don't grow too large. So you can actually train massive networks as long as you want, and they won't do, catastrophically bad. So, but yeah, this has been very technical, but that's I think that's the core behind deep learning, is to actually do have regularization regardless of how large you make the models. And right at the beginning of statistical learning theory, there are always two ways of simplifying your model. It could either be so simple you can't possibly fit your training data, right? Which is the intuition behind why, fitting all your training data is bad. But the other way is regularization. It's just as good, and you can fit all training data always with the RBF kernel, right? So it's not actually sort of a red herring about whether you can fit all of your training data.
Zena.
Hello. I just want to acknowledge before Zena that this has been the first time that we've had 0 women other than me on screen, and I'm very unhappy about that. But okay, Zena, go ahead.
I can't hear you, Zena.
You're muted, or maybe your microphone is not connected because you don't seem to be muted. I can hear John's book, but I can't hear Zena. No, that was a joke, so that while Zena is managing his microphone, we have entertainment. Actually, John, one day we should record all of these sounds. I will literally make music with it.
Can you hear me now?
Yes.
Okay,
Yep.
Hi, Simon. Simon and I go way back, so it's good to see you. So I had a few questions, and they're mostly about your method. We didn't talk so much about your actual method. And in particular, there's part of your method where you take data and you generate more data from that data through these transformations. And so my first question is, at a high level, why is that necessary? Doesn't your data contain all of the information in it to do those transformations? So why do we have to have this intermediate step? My second question is there something special about these particular kinds of transformations that you do, right? So you're doing kind of, as I understand it, translations and cropping and so on. If I've got some other non-image type data, how could I generalize this idea to this other non-image data? Is it that these are kind of natural transformations that you find in the world, or is it something else? And then my third question on the same point is going to this discussion about human style learning. Is there any evidence that this kind of contrastive divergence from this kind of multiplied data corresponds to anything that humans do?
Yeah, so I think those are all very good questions. So the first question, if I understand correctly, is why is it that we need to do this funny stuff with the data to learn a good representation? And I think there's no good answer that we have right now. So it seems like there are different ways of trying to learn a representation without labels, and this happens to be the approach that works best. But it's not the only approach that you can take, and there are other approaches that also seem to work quite well, but they're even more computationally expensive than this one. So for example, OpenAI has a paper where they try to train a model so that it predicts the next pixel based on all the previous pixels in an image. So this is different from what we're doing. We're just taking 2 different views of an image, and they're actually trying to predict each pixel in an autoregressive fashion. And they've shown that they can take the internal representations of that model, and they also work quite well. And it doesn't need to take 2 views out of the image. They're just predicting an image pixel by pixel. But I guess, yeah, I think it's still an open question why the things that work, and also why other approaches don't seem to work as well here. So your second question was about the specific augmentations, the transformations that we use. And so I think we actually put a lot of work into tuning those, but they're still pretty simple. I mean, so one of the reasons our approach works better than previous approaches is that we recognize that the color distortion is actually extremely important to get these models to learn a good representation. So if you have no color distortion, the representation is just terrible. And by making it stronger, you can somehow learn a better representation. And
So you mean like taking an image and distorting the color of that image?
Yeah.
Okay.
Yeah. So we take two crops out of the image, and then we distort the colors of each crop. And the color distortion step is very important because otherwise the model can kind of learn this shortcut where it can identify whether two images or two views came from the same image just by the color histogram. So just by like looking at where the peaks are there, it seems like you can do a reasonably good job of identifying the source image. And if you let the model do that, it will learn to do that, and then you'll learn a representation of the color histogram, which is not very useful for doing any other kind of task. Zena, you're muted.
There must be like some boundary on the transformations that are valid, right? Because, you know, like a counterexample could be that you take your image and then you transform it into something which is from another class, right? Conceptually, which you wouldn't want to do, right? You want these things to be together as opposed to apart. So what is the boundary upon which you say, okay, these are the valid transformations that I'm willing to apply to multiply my data set versus these things would actually be detrimental?
Yeah, I mean, I think like in practice, it's kind of empirical. So we didn't try any transformations that would really change one class into another. But I guess I can imagine that would be possible and that you wouldn't want to use those. So can you remind me of your third question?
Yeah, well, that was just like, does this correspond to human learning in any way that we know of?
Yeah, I think that's a good question. And I think the answer is, at least as far as I understand it, no. There's no evidence that humans do anything exactly like this. Although I guess you can imagine that maybe like in the process of making saccades around, like you are actually getting something kind of like different crops of like your visual input. And like maybe that's something like this method, but I think we're kind of making things up here, and it seems like John is not happy with this.
Cool. I'm happy. Thank you.
Thanks, Zena.
John, you're muted this time.
No, I'm just saying, if Zena's happy, I mean, what else could one possibly want?
Zena happiness, world peace.
Did you say Zena happiness, world peace?
Yeah. That's John's order.
Where's the bird's getting vaccinated?
Yeah, I'll be happy then.
Yeah. Who else is asking questions here?
So there are a lot of questions there that I think many people couldn't show up, but maybe we can read their questions at least. Not sure if that's, somebody says, Shayan says many images from ImageNet contain objects from multiple classes, like chairs often have people sitting on them. I'm not sure if that's a question, but I guess that was a reference to the last conversation. In the questions, there is, I'm going to read the smaller questions because if it's long, a subset of pictures of a dog might not include any part of a dog. For example, it might just contain floor or sky. Do you control for this?
Yes,
This is a question from Jason Webster.
We don't do anything special when we train the algorithm. Like it is true that like maybe your pictures of dogs, when you take crops out of them, you'll often just get a piece of grass or a piece of sky. But like that could still be useful because I guess like you'll end up learning that like it could be useful in a way that maybe is kind of cheating when you're performing this task, because you'll learn that maybe dogs tend to be on grass with sky nearby, and that's something that's useful if you want to go classify dogs. So yeah, we don't do anything special, and it seems like maybe there's not necessarily a reason to do anything special if your task is to classify these images.
Okay, so the answer is no. And then Kevin Patrick Coaster, I hope I pronounced it correctly, says, do you extract any information about what these models are considering as important features for classifying images? Is it known whether Sinclair, for instance, prioritizes specific image features that other models do not to gain its improved performance? Could this type of information be useful for guiding future models? Sorry if this is implicit in the talk.
Yeah, so I think like understanding what features of images deep neural networks use is generally challenging, and we haven't really made any attempts at doing that with our models.
Neil, so in response to that question, sometimes people respond to questions, so they add questions. Neil Traft says it seemed like he was saying that Sinclair was not really learning significantly better representations than other models, but would be interesting to hear him. So their question is whether Sinclair is learning significantly better representations than other models.
Yeah, so I guess like based on our studies of the behavior of Sinclair models and the studies of other researchers, we don't think the representations that these models learn are substantially different from representations of supervised models. But again, like it's very difficult to actually measure this in any particular way.
Gotcha. Next question is from Cheyenne, and they ask, would there be any advantage to using a data set that is more representative of normal visual experience? For example, rather than photos, we use videos with saccades and maybe microsaccades and foveation.
So I think there are a few papers that have tried training self-supervised learning techniques on data that's basically created from like helmet-mounted cameras on babies. And I think they find that it is possible to learn like reasonably good visual representations in that way. But I'm not entirely sure of the details of those papers. I mean, I think like if these data sets actually worked better than ImageNet, then people would be using them.
Thank you. David Murphy asked a longer question, so I'll try to read the whole thing. I'm wondering, given the characteristics of the loss in contrastive learning, repulsion, or attraction of representation, whether this is applicable hierarchically for fine distinctions in class. For example, say two images of satellites. They are both satellite class, but also different. Can we use the representations learned here to understand coarse or fine class membership?
So I think like if it does a decent job on ImageNet, it kind of has to learn a representation that incorporates both fine and coarse distinctions, because I guess ImageNet is constructed so that it has like this fine-grained subset of classes, which are just different breeds of dogs, like 120 breeds of dogs. And so a model to do well on ImageNet has to be reasonably good at differentiating all those dogs. But it also has like another set of classes. Many of the other classes are not so fine-grained. For example, I think there's like a sports car class, and that's like all of the sports cars have to go into that class. So I think like the model has to learn a representation that kind of is hierarchical in the sense that stuff that belongs to the same coarse class is closer together, and stuff that belongs to the same fine-grained class is even closer together.
But do you know that? In other words, is it true that when you train on 100 types of flower or car versus the different categories, it could be that we know that you're within class versus across classes, but maybe at some low level, pixel level, you can still get it done. In other words, it could be bottom up in all those cases, right? I mean, you don't know for a fact that there's a little bit more coarse graining in ImageNet versus what happens when you have to classify 100 flowers or 100 cars. I mean, there's not a qualitative difference in how it's being done, right? You yourself said the representations end up being very similar. So how do you know that you seem to be implying that the system understands within class differences and across class differences in some qualitative way? It just all seems the same thing to me.
Yeah, I mean, I guess like if you actually just look at the representations, if you like do dimensionality reduction on them, you'll see that like the biggest distinction that jumps out is like this animate-inanimate distinction, which suggests that at least it has captured some notion of being hierarchical. But I agree that like maybe it's possible to do these coarse grain distinctions just by doing all the fine grain distinctions, if that's what you're implying.
Yeah, that is what I'm implying, and I just want to know whether you know for sure that that isn't the case. I mean, I'm just want to make sure that we don't assume a difference when it's just all fine grained, and there's just enough difference at the fine grain level that you can keep on going within class, just like you were across class.
I mean, I think you wouldn't necessarily generalize well in that situation. Like you would need more data to generalize well if you only have a fine-grained representation. Because you need data from each of the fine-grained classes then instead of just needing data from the coarse-grained class.
And can you just remind me how good is the generalization?
So our model is as good as a state-of-the-art image classifier from about probably 4 or 5 years ago, if you look at our best model, an image classifier that uses the labels. I guess compared with humans, it's really hard to judge because humans are not that good at classifying 120 different classes of dogs, and no one has ever individually looked at all of the images in ImageNet.
Mm-hmm. And if you put in that set of 100 flowers a sort of cloth flower or a flower made out of metal, what happens then? In other words, does it make a mistake if you give it a metal flower or a cloth flower when it was only trained on real ones? Is it does well? It doesn't make a mistake. Is that right?
That sounds like the elephant textured cat, right?
Right. So I'm just asking, what happens when you give it, you know, a fake flower, but it's obvious to a human that it's fake? What will it do?
I mean, I think for any individual image, it's hard to say what it does, but I think like in general, the more data you train it on, the better it will do on those kinds of cases. And so like earlier in the talk, I discussed like these out of distribution robustness data sets where people have tried to collect images that belong to the same classes that are in ImageNet. And I don't think there are any data sets of metal flowers, but there are data sets. There is a data set that contains sketches of every class in ImageNet. And that's also like something where the models that perform better on ImageNet will perform better on those sketches as well.
Mm-hmm.
Simon, do you generally believe that this approach, just scaled up to more and more data, is maybe not this particular approach, but this broad class of approaches is kind of the way forward, the future, inevitably?
I mean, I'm not sure. I wouldn't necessarily commit to that, but I think that we have not hit the wall yet. So the question is basically, can we come up with something that scales like substantially better than what we have now? And it's not clear to me that we can.
Mm-hmm. Scales in terms of how much data you can consume, or in terms of what?
I guess in terms of the amount of computation that you need to learn a good model. Mm-hmm. So yeah, it could mean amount of data that you can consume. As I said earlier, I think we're in the regime where we have an unlimited amount of data, or an effectively unlimited amount of data. And the real problem is just getting that all into a model in a way that we can use that model for other stuff.
Cool.
So Rosa asked the question. I don't know if she, Zena, you have an echo. Sorry.
Sorry.
So Rosa asked the question, and in the chat, I don't know if they're still here, but I can ask it. And I think you answered it. She asked, so the difference is whether the unsupervised models learn from data that is more similar to what humans get. Oh my God. Oh, Rosa is there. Oh, already answered. Good. Okay. So this has been already answered. That's good. As to Andrew's point about finding hierarchy in ImageNet models, there's also a lot of critique of the notion of hierarchy and whether it's really hierarchy in CNNs. I'll send the paper while somebody else is asking something.
I think we're good. I think we've covered most of the questions. I think,
great.
There's a lot of interesting topics that we've discussed, and it's been 2+ hours. And
in that sense, in that case, I will just first thank Brad and Claire for being behind the scenes and helping. And Claire has been helping a lot with changes in the schedule. And as a reminder about the changes and Eva and Worldwide Neuro. And as a reminder, next week we are going to have Danny Bassett and Perry Zern. And this book, Curiosity and Power, is a published book already by The Politics of Inquiry. That's what it says. That's already published by Perry Zern, who's actually the twin of Danny Bassett, which is very exciting. And they just submitted a book together called Curious Minds. So it's going to be written by two authors, one of whom is a neuroscientist and the other one a philosopher. And it's going to discuss issues around curiosity, power, brain, etc. So it's going to be very interesting, more broad discussion. And I hope that you guys can join it next time. I guess that's it. Yeah, thank you, Jovo, for sending that tweet. Yeah, exactly. So if you want to take a look at the tweets.
And thank you, Simon. That was awesome.
Thanks, Simon.
Thank you so much, Simon. Yeah. Thanks
for inviting
Thanks, everybody.
Ciao.
Have a nice weekend.
Bye.
Have a nice long weekend.